Welcome back, everyone. In this video, I'll be going over the lecture for the mean value theorem. Now, for the mean value theorem, we really need to talk about something called Rolle's theorem first, because Rolle's theorem actually is an easier type of the mean value theorem. But if we were to go through and actually prove the mean value theorem, you actually prove Rolle's theorem first. And Rolle's theorem is also going to be interesting in the sense of if you were trying to find, let's say, where the critical points, the critical values of a function, but you didn't really have a formula, you just had a graph, Rolle's theorem would at least tell you when you might have some, just from looking at the graph. Of course, at this point, we should have a little bit of understanding about what that means, but we'll go ahead and jump into it and see what it says. All right, so Rolle's theorem says let f be a function satisfying the following three conditions or hypotheses. So f is continuous on the closed interval a to b, so it's continuous at the endpoints. F is differentiable on the open interval a to b, so it doesn't have to be differentiable at either of the actual endpoints. An example of something that might be continuous at the endpoints but not differentiable at the endpoints is something like a square root function. And we'll actually be able to see that if we computed the derivative and solved the formula. And then number 3 here is that the f of a equals f of b. So if you have the graph and you're looking at the y value for at x equals a and x equals b of your function, they are the same. So I've kind of got a setup here. But what the ultimate conclusion is that there is a number c between a and b. So that's how we read this, a number c in a and b with parentheses. So c between a and b such that the derivative equals 0, f prime of c equals 0. Now what's really important here is that you have to satisfy the first two conditions. Well, you have to satisfy all the conditions, but if you can definitely draw pictures where these y values are equal, but if you don't satisfy these two conditions, then this doesn't need to happen, right? But just to sort of explain how this is done, if you were to prove it, the main idea is that you have these y values and our function's continuous, meaning as I draw this from going left to right, I can make it look however I want. I just need to make sure I don't pick up my pencil or whatever I'm writing with to graph it. But also it must be differentiable, which means there's not going to be any sharp points like an absolute value. So there's tons and tons of examples, but something could be like this. That could be something that is continuous because I did not pick up my pencil or the marker as I drew it. It's differentiable because I don't have any sharp points. And I had originally had the restriction on f of a equals f of b. So the y value at the start and end are the same. Now, we know a little bit about the derivative equaling 0 is if you have a maximum or a minimum, local maximum or a minimum, then the derivative is automatically 0. So just as this picture has drawn, this would be a point where f prime of c equals 0. So this could have been a c value between a and b. Now, this theorem does not say there's only one. What it says is there's at least one. And this way I've drawn this graph, there is more than one point where the derivative is 0 because we have a maximum up here. And, maybe we flatten out over here, maybe we actually don't, so the derivative may or may not be 0 again. But the point is, with Rolle's theorem, if your function is continuous on the closed interval, if it's differentiable on the open interval, and the y values are the same at the ends, then you do have a spot where the derivative is 0. Right. So what I'm going to go ahead and do is there's not a lot you can do with this theorem directly. It'd have to be pretty indirect, and those problems are really more for like an advanced calculus type of course. But we can just make sure we understand what the hypotheses or what the conditions are saying. So this problem I have here is just a quick true or false. You don't have an actual function formula, which means you have to understand what you're looking at and compare it to the hypotheses. And it says true or false. If f is differentiable and f of -2 equals f of 2, then there's a number c such that the absolute value of c is less than 2 and f prime of c equals 0. Right? Well, this is asking us, is this the kind of setup for Rolle's theorem? So we would have to see if we satisfy these three things, because the conclusion here is we want to have a c value that's absolute value is less than 2. Now the way you can think about this, because it shows -2 and 2 for us to be the x values, a is -2 and b is 2. This is just saying c is between a and b. Right, so if the absolute value of a number is less than 2, that means it's bigger than -2. It's also smaller than +2. All right, and you can just kind of think about it. But the way some people might think about the absolute value here is the distance from 0. So if you draw your number line, the distance from 0 is less than 2. That means it could be up to 2. It could be back to -2. It's somewhere in there. All right, but ultimately it's asking us, do we have a c between a and b where the derivative at f prime of c equals 0? That's the exact conclusion here. We want to make sure that this preliminary stuff is satisfying all this or not. If we break just one of the rules, then it doesn't work. So we have to break them all. Or sorry, we have to satisfy them all. So do we have continuity? Do we have differentiability? And do we have that the function values are the same? Well, the third one might be the easiest one to see. Just right away, it does say that the function values are the same. F of a equals f of b. Just remember, a is -2 and b is 2. So we automatically satisfy that one. Now, another one that we can just get from reading the problem is that second one here, because it says f is differentiable. Well, what saying f is differentiable means is that f is differentiable on the entire real line, on -infinity to infinity. Right? It's not saying specifically any other type of interval, which means we just assume it's differentiable from -infinity to infinity. Well, that means it's automatically differentiable from -2 to 2. So we'd have to be differentiable on the open interval from a to b. A is -2, b is 2. And if it's differentiable from -infinity to infinity, that is satisfied. The way you can think about this is that the interval -2, 2 is inside where the function is differentiable itself, -infinity to infinity. All right, so the last one that might be a little more indirect, but it's actually true, is the continuity. Because wherever your function differentiable, it's automatically continuous. So that's one thing that when we talked about the definition of differentiability, we needed continuity. So differentiable implies continuity. What that means is that since it's differentiable from -infinity to infinity, it's also continuous on -infinity to infinity. So I'll abbreviate differentiable DIFF. So since it's differentiable on the interval -infinity to infinity, it is also continuous on -infinity to infinity. Right. Now, maybe we're kind of using a lot of theoretical things here because we don't have an actual formula, but the idea is that really all this is saying is pretty much exactly this picture, with a being -2 and b equal 2. We satisfy all three conditions, all three hypotheses, which means that the result is satisfied. So we'd say this is true. Right, so just again, a quick recap. We checked that all these three results are satisfied. The problem was asking us, do we have all three conditions satisfied so we can conclude this? And we figured out, yes, we do. All right, now the mean value theorem comes from Rolle's theorem. It's a little more general. It says, let f be a function that satisfies the following hypotheses. And it's actually the same first two hypotheses as Rolle's theorem. It says f is continuous on the closed interval a to b, and f is differentiable on the open interval a to b, then the conclusion is there's a number c in between a and b such that the derivative at c equals f of b minus f of a over b minus a. So the main thing is that in this one, we are dropping the assumption that f of a equals f of b. Now, if f of a did equal f of b, then this numerator would be 0. And so our derivative, we would be saying our derivative equals 0. So this is a generalization of Rolle's theorem. And the mean value theorem is more widely used, and we will see that with our example that we can do a little bit more with it. But I wanted to go ahead and draw a picture just to simulate what this is saying. So I'm going to kind of do the same thing. I'm just going to draw a picture of my function. Just to make it easier to see the picture, I'm going to draw this one less scattered and more straightforward. So let's say our function looks like this. This is y equals f of x. Well, one thing you want to notice is that what this number represents over here, f of b minus f of a over b minus a, this is just like y2 minus y1 over x2 minus x1. This is the slope of what we call the secant line. And we haven't done a lot with the secant line, and we're not going to do much with it going forward. But the point is, if you connect these two points by a straight line, the slope of this is the slope of the secant line. Secant line is just the line when you connect 2 points straight together. And what this theorem is saying, mean value theorem is saying, is that we have a number between a number c between a and b, something down here where the tangent line, the slope of the tangent line is the same as the slope of the secant line. So they're parallel. And it would look maybe somewhere around here. The tangent line at that point goes like this. And that would be the tangent line. So this would be our c value down here. But the point is, because we're saying the slope of the tangent line equals the slope of the secant line, they are parallel. Right. Now, in general, the mean value theorem is used to kind of come up with an assumption, come up with something that maybe you, once again, you don't have the actual function formula, but you want to know if something's true. So maybe you have a graph and you're keeping track of how far you are away from house. Maybe you're driving, walking around the city, who knows, but you're driving around, and let's say you want to know how fast am I going at some point. Well, you don't constantly take your speed or look at it. So the graph of your distance from your house might be exactly this. So let's say, after 1 hour, you're 10 miles away. And at B, let's say 2 hours, you're 30 miles away. Well, in that hour, you went 20 miles further, but you could have gotten closer. You could have gotten farther away and come back. What the mean value theorem is saying is at some point, you were going 20 miles per hour. Even though you never looked at your speedometer, you have no idea. The idea is, because you traveled 20 miles in an hour, that at some point you were going 20 miles per hour. And that can be a really powerful feature because, once again, you're just looking at a graph, or you're just even really taking data points, but you know that you can connect it in a curve, and you're coming up with a pretty big conclusion. Right, but what we're just going to go ahead and use it just really like the first one. We want to make sure we know that functions satisfy the conditions or the hypotheses of the mean value theorem. But because the derivative is not going to be 0 all the time for the mean value theorem, because it's just going to be the slope of the secant line, what we're going to have to do is actually find that c value if all the conditions are met. Right, so number 1 here. And this is the only one, because pretty much with the mean value theorem, this is really all we can ask. It says, does the function f of x equals x over 2 satisfy the hypotheses of the mean value theorem on the interval 1 of 4? You absolutely have to be given an interval when you talk about the mean value theorem or Rolle's theorem. And it's asking, does this function satisfy the two hypotheses? Well, this one, since we have an actual function, we have to check. Is it continuous? Continuous on the interval 1 to 4? And also, is it differentiable on the open interval 1 to 4? Right? And this can play a big role when you have the open interval compared to the closed interval. It might not matter in this problem. Well, how do we check continuity? We just check the domain. So that's something we talked about before. It's just when you want to check the continuity, just check the domain. Because we have a fraction here, basically the only time we're not going to be continuous is when the denominator is 0. So we know to do that, we set the denominator equal to 0 and solve it. And we get x equals -2. All right, x equals -2. This is the only x value where f is not continuous. All right, so that's great. That's the only x value where the function is not continuous. Is it between 1 and 4? No, -2 is not between 1 and 4, which means this is satisfied. I don't know why I put a question mark there. That should just be a period. But our first condition is satisfied. Yes, it is continuous from 1 to 4 because the only spot we're not continuous is x equals -2, and that's not between 1 and 4. Now to check differentiability, you have to do the derivative. So we've got to do the derivative. You can't just say, oh, well, it's continuous, therefore it's going to be differentiable. You have to do the derivative. And then once you do the derivative, then you check like continuity. Do we have anything that can't happen? All right, so let's go ahead and do the derivative. F prime of x equals the derivative of the top is 1 times the bottom, x plus 2, minus the top, x, times the derivative of the bottom, which is just 1, over the bottom, x plus 2, all squared. Go ahead and simplify. So on the top, we've got x plus 2 minus x. Well, that's just actually 2 because the x's go away. We have 2 over x plus 2 squared. Okay, so this is the derivative formula. It is completely simplified. There's nothing to possibly simplify on the top because it's just the number 2 and it doesn't cancel out with anything on the bottom. So the last thing we want to do is ask, is this function differentiable? Meaning, if we look at our derivative formula here, does this defined in the interval 1 to 4, meaning we can kind of think about it as continuous from 1 to 4. We don't want to actually say that because the derivative doesn't have to be continuous, but is 1, 4 in the domain of f prime? Well, it's pretty much like answering the same question with continuity, because with a lot of our functions, and this is going to be one of them, it has the same format as the original. It's a rational function. When you answer continuity, you're just checking the domain. So all we're asking here is, if we figure out what numbers are not in the domain here, is it between 1 and 4? Well, to figure out the domain, we know we do the same thing as before. It doesn't matter if it's the original function or the derivative because it's just another function. But we just set the denominator, x plus 2 squared, equal to 0. And if you solve this, you should not be surprised that it would be the same as solving this because you do the square root, that gets rid of the square root, and you're solving the same equation. So we solve this and we get x equals -2. And -2 is the only number not in the domain of our derivative. So x equals -2 is the only number not in the domain of the derivative. All right, so what is that telling us? Well, -2 is not between 1 and 4, which means we satisfy both conditions. This is also satisfied because -2 is not between 1 and 4. Or we could say since -2 is not in the open interval 1 comma 4, this condition is also satisfied. We satisfy both conditions. Now that means what? Well, now that means we want to actually find the numbers C that satisfy the conclusion of the mean value theorem. So what are the C values? Well, we have the derivative. So we want f prime of x to equal, well, really we want f prime of c, right? So let's go ahead and actually use the correct letter. We want f prime of c to equal f of b minus f of a over b minus a. And here, our first number 1 is the a, and our second number b, 4 is the b. So we want f of 4 minus f of 1 over 4 minus 1. And now you might want to just figure out the f of 4 and the f of 1 on the side because our function's already kind of messy. So I'll go ahead and do that on the side and then plug them in. F of 4, remember you're plugging into the original function. It's x. You scroll up a little bit. It's x over x plus 2. So when we plug in 4, we get 4 over 4 plus 2, which is 6. And that simplifies to 2/3. And f of 1 equals 1, because it's x over 1 plus 2, which is 3. And that's already a simplified thing. So we've got f of 4 is 2/3 minus f of 1 is 1/3 over 4 minus 1, which is 3. You can simplify the top because we already have a common denominator. 2/3 minus 1/3 is 1/3. So 1/3 over 3. And then it's up to you how you finish this up. You can do keep, change, flip. You can think about the 3 on the bottom being 3 over 1. And when we do that, we've got 1/3. Just change the division to multiplication and flip the bottom fraction to another 1/3. And we get 1/9. All right, so what is that telling us to do? We want the values of c that where the derivative is 1/3. So we want f prime, or sorry, 1/9, not 1/3. So we want the number c to equal 1/9, the derivative. And remember that c must be between 1 and 4. Because you could get more than one answer. Well, we can get more than one answer anyway, but we only care about the interval 1 to 4. So if it's not between 1 and 4 for our c value, then we don't really want to use it. Well, luckily for us, we've already got the derivative formula done. So f prime of c. Well, this is f prime of x, so we can just plug in c for x. We get 2 over c plus 2 squared equals, and we want it to equal 1/9. Now you want to solve this. We can cross multiply to get rid of the denominators. We get 2 times 9 on the left, because the 9 comes up here. We get 18 equals 1 times c plus 2 squared. Now you want to solve this for c. The best thing you can do is go ahead and do the square root of each side. When we do the square root, because this is not 0, you do the plus or minus, and you get plus or minus the square root of 18 equals c plus 2. And pretty much one more step to get c by itself is to subtract the 2 from each side. Now, whenever I have a plus or minus already on something, then I like to put the thing I add or subtract in front of it. So I have -2 plus or minus. We can go ahead and simplify this a little bit because 18 is 9 times 2. The square root of 9 is 3, so this is 3, but the 2 is stuck inside the square root. And what we just found the 2 c values that might work. So the 2 possible c values are negative 2 plus 3 times the square root of 2, and negative 2 minus 3 times the square root of 2. Well, you definitely need to make sure they're between 1 and 4. If neither one is, well, then there is some mistake because there has to be at least one, but we don't know if they both are or not. So let's go ahead and check. Just do negative 2 plus square root of 3 times the square root of 2. That is between 1 and 4, which means we will keep this one at least. What about the one with the minus? Well, you can kind of just look at it, but we have negative 2 and then we're subtracting something, so it's not going to be between 1 and 4, and it is not. It's negative 6 point something. So the only answer is for C is negative 2 plus 3 times the square root of 2. Yeah, it's a lot of work because what do we have to do? We have to figure out what the slope of the secant line is. We have to do the derivative and set it equal and solve that equation. And you can only do that really after you figure out that the first two conditions are satisfied. Right? But if the first two conditions aren't satisfied, one thing to really emphasize here is that you might still have a C value, but you're not guaranteed it. And if you're not guaranteed it, you don't really want to look for it. So that's the point. You want to make sure you're only trying to look if you are guaranteed. Right? But that's it for this section. Really, once again, it's kind of knowing what the mean value theorem is and how to make sure you're reading it correctly, hypotheses are satisfied, and then you can actually go through and actually compute it. But I will see you in the next video.